Hello everyone. Today we will going to see some practice questions from the topic electrochemistry, and this is part 6. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any of images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. This is our index slides. So we will going to see the practice questions from question number 39 to question number 46. Let's start with the question number 39. Aluminium oxide may be electrolyzed at 1000 degrees Celsius to furnish aluminium metal. Atomic mass will be 27 unit and 1 Faraday is given as 96500 coulomb. The cathode reaction is aluminium 3 positive plus 3 electron giving us aluminium. To prepare 5.12 kg of aluminium metal by this method, required electricity will. So we have to find out the required electricity in the process. Options are 5.49 times 10 to the power 1 coulomb, 5.49 times 10 to the power 4 coulomb, 1.83 times 10 to the power 7 coulomb, or 5.49 times 10 to the power 7 coulomb. You have 10 seconds to solve this question. After that, we will see the answer. Okay, now let's see. The correct answer is option D, that is 5.49 times 10 to the power 7 coulomb. Now, the cathode reaction is given, which is aluminium 3 positive plus 3 electron giving us aluminium metal. And from Faraday's first law, we know that W, weight, is equals to Z times Q. W, where W is amount of metal, which is equals to 5.12 kg. It is given in the question, right? That to prepare 5.12 kg of aluminium metal required. So basically, weight will be 5.12 kg. We will convert it into the grams. So 5.12 times 10 to the power 3 grams. Q in this formula, Q is charge. Z is electrochemical equivalent, and Z is also equal to equivalent weight divided by the 1 Faraday, that is 96500. Okay, now let's put the values. So Z is equals to atomic mass upon number of electrons times 96500, because we just said that Z is equivalent weight divided by 96500, right? So equivalent weight, we can write it as atomic mass divided by the number of electrons, and in the denominator we have 96500. So atomic mass is 27 unit, it is given. Number of electrons is 3 in the reaction, which is given, and 96500 is a constant. So Z value is this. Now we put it in the initial formula, that is W is equals to Z times Q. So W is equals to 5.12 times 10 to the power 3 gram is equals to Z value, which we just have calculated, times Q. And Q is the electricity which we need to calculate, right? Which is we have asked in the question. So Q will become equal to 5.12 times 10 to the power 3 times 3 times 96500 divided by 27 coulomb. Okay, and on solving this fraction, we have Q is equals to 5.49 times 10 to the power 7 coulomb. Okay, so this is our final answer, and thus our D option is the correct answer. Okay, now let's move to the next question, question number 40. For a saturated solution of AgCl at 25 degrees Celsius, specific conductance is 3.41 times 10 to the power minus 6 ohm inverse centimeter inverse, and that water used for preparing the solution was 1.6 times 10 to the power minus 6 ohm inverse centimeter inverse. The solubility product of AgCl is. So we have asked the solubility product of AgCl compound. We have given the lambda infinity equivalent of AgCl is 138.3 ohm inverse centimeter inverse equivalent inverse. Okay, so we have given the specific conductance value for AgCl. We have given the specific conductance value for the water which we used to prepare the solution of AgCl. We have to find out the solubility product of AgCl. Options are 1.31 times 10 to the power minus 5, 1.74 times 10 to the power minus 8, 1.72 times 10 to the power minus 10, 3.61 times 10 to the power minus 3. So you have 10 seconds to solve this question. After that, we will see the answer. Okay. Now, let's see. The correct answer is option C, that is 1.72 times 10 to the power minus 10. So, for AgCl, molarity is equal to normality, and actual specific conductance we calculate. So, it will be specific conductance of AgCl minus specific conductance of water, because we have given the specific conductance for both the water and AgCl. So, the actual specific conductance will be the difference of these two. So, it is equals to 3.41 times 10 to the power minus 6 minus 1.6 times 10 to the power minus 6. We take 10 to the power minus 6 as common, and this difference is coming out as 1.81 times 10 to the power minus 6 ohm inverse centimeter inverse. So this is the specific conductance. Now, for a saturated solution of sparingly soluble salt, lambda equivalence is equals to lambda infinity equivalence. This is a important concept. So for saturated solution of sparingly soluble salt, lambda equivalent is equals to lambda infinity equivalent. Okay, and solubility is equals to concentration, that is molarity. So lambda infinity equivalent is equals to 1000 times specific conductance divided by the solubility. This is the formula. So we just put the value. We have given the lambda infinity equivalent, which is 138.3, is equals to 1000 multiplied by specific conductance. We just have find out this actual specific conductance. It is 1.81 times 10 to the power minus 6 divided by the solubility, and solubility is S. So the only variable present in this equation is solubility S. So we just find out this. It will be 1000 times 1.81 times 10 to the power minus 6 divided by this lambda infinity equivalent, that is 138.3, and it will be equal to 1.31 times 10 to the power minus 5 mole per liter. Okay, so solubility will be equal to this one. Now, this is the complete reaction. AgCl giving us Ag positive plus Cl negative. So, therefore, Ksp, we have to find out the solubility product, right? So, Ksp for this reaction is Ag positive concentration times Cl negative concentration, which is equals to S square in the terms of solubility. We have the solubility, so we just take the square of that, and it is coming out as 1.72 times 10 to the power minus 10 mole square liter inverse square. Okay, so this is the solubility product we get from the solubility, and thus our C option is the correct answer. Okay, now let's see the question number 41. The addition storage cell is represented as this: iron, iron oxide, potassium hydroxide, Ni2O3, NiO, and nickel. The half cell reactions are Ni2O3 plus H2 plus 2 electron giving us 2 NiO plus 2 OH minus. E naught for this reaction is this one, and FeO plus H2O plus 2 electron giving us Fe plus 2 OH minus. E naught for this reaction is coming out as this one. So, what is the maximum amount of electrical energy that can be obtained from 1 mole of Ni2O3? So what we have asked? We have asked the amount of electrical energy that can be obtained from 1 mole of nickel oxide. Options are 127 kilojoule, 245.11 kilojoule, 90.71 kilojoule, or 122.55 kilojoule. So you have 10 seconds to solve this question. After that, we will see the correct answer. Okay. Let's see. The correct answer is option B. That is 245.11 kilojoule. So E naught for the FeO Fe is minus 0.87. It is given. And E naught for Ni2O3 to NiO is given as plus 0.40. It is also given in the question. And we can reverse this one. So E naught for Fe to FeO is plus 0.87. And what we will do, at anode we know this reaction is happening, Fe plus 2OH minus giving us FeO plus H2O plus 2 electron. And at cathode this reaction is happening, that is Ni2O3 plus H2O plus 2 electron giving us 2 NiO plus 2 OH minus. The overall reaction will be sum of these two anode and cathode reactions. It will be Fe plus Ni2O3 giving us FeO plus 2 NiO. And hence the E naught cell will also be the sum of these two E naught of these two anode and cathode reactions. It will be 0.40 plus 0.87, which is 1.27 volt. Now delta G naught is equals to minus NF E naught of cell. This we know, right? This is the relationship between del G and E naught of cell. So del G naught we can write it as minus N is 2. N is 2. So 2 times F is 96500, E naught of cell which is coming out as 1.27, so 1.27. We take the multiplication and it is coming out as minus 245,110 joule. We can write it as 245.11 kilojoule. Now we also know that del G naught is equals to minus W max, minus of maximum work done. So we can we have the del G naught which is minus 245.11. We just put it here. Minus minus will become plus, and the maximum work will be equal to 245.11 kilojoule. This is our final answer, and the correct answer is option B. Okay. Now let's move to the next question. Question number 42. An inaccurate ammeter and silver colorimeter is connected in series in an electrical circuit, through which a constant direct current flows. If emitter reads 0.6 ampere throughout 1 hour, the silver deposited on colorimeter was found to be 2.16 gram. What percentage error is reading in the ammeter? Assume 100% current efficiency. Options are 1%, 0.54%, 0.06%, or 10%. So you have 10 seconds to solve this question. After that, we will see the answer. Okay. So let's see. The correct answer is option D, that is 10%. So weight upon equivalent weight is equals to I times T divided by the 96500. Okay. Or you can put it as 2.16 is the weight divided by equivalent weight, which is equivalent weight is molar mass upon the number of electrons. So equivalent molar mass is given as 108, because for silver the molar mass is 108 divided by the number of electrons involved, which is 1, is equals to I times T. T is 1 hour, it is given. Okay, so 1 hour converted into seconds, it will be 60 times 60, 3600 divided by 96500. And from this equation, I is the only variable, so I is coming out as 0.54 ampere. Now, the error in the reading of emitter is giving as how can we calculate the error? So basically we have given the ammeter reading, right? But actual reading is coming out as 0.54. So what is the error? Error will be the reading given 0.6 minus the actual reading 0.54. It is 0.06. Now the percentage error will be the error coming out divided by the initial reading multiplied by 100. It will be equal to 10%. Okay, so percentage error is 10%, and thus D option is the correct answer. Okay, now let's move to the next question, question number 43. An aqueous solution of NaCl on electrolysis gives H2, Cl2 and NaOH. According to the reaction, 2Cl negative plus 2H2O giving us 2OH minus plus H2 plus Cl2. Now, a direct current of 25 ampere with a current efficiency of 62% is passed through 20 liter of NaCl solution, which is 20% by weight. How long it takes to produce 1 kg of Cl2 molecule? Okay, we have to calculate the time. Options are 30.20 hour, 12.17 hour, 48.71 hour, or 14.61 hour. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. The correct answer is option C, that is 48.71 hour. So the redox changes are at anode 2Cl minus giving us Cl2 plus 2 electron, at cathode 2H2O plus 2 electron giving us 2OH minus plus H2. Oxidation and reduction. Okay. Now, we know that weight upon equivalent weight is equals to I times T divided by 96500, and weight of Cl2 is given as 1 kg, which is 10 to the power 3 gram, and equivalent weight of Cl2 is 35.5 gram. Okay, so I, that is current, is 25 ampere. So 25 with the 62% efficiency. So 25 times 62%, that is 25 times 62 divided by 100. It is coming out as 15.5 ampere. Okay, so we have I value, we have equivalent weight value, we have weight value. We just put it in this equation. So T we have to find out, time we have to find out. So it will be 10 times 10 to the power 3 times 96500 divided by the equivalent weight times the current. So on solving, it is coming out as this much in seconds, and we convert it into hour. So T is equals to 48.71 hour. How we do it? So from the seconds we divide it by 3600, 60 times 60, and it will convert it into hour. Okay, so that's thus our C option is the correct answer. Okay, moving to the next question, question number 44. Zinc 2 positive, A is 0.1 molar. Salt bridge, Fe2 positive, A is 0.01 molar, Fe. The EMF of the above cell is 0.2905 volt. Equilibrium constant for the cell reaction. We have to find out the equilibrium constant. Options are 10 to the power 0.32 divided by 0.0591, 10 to the power 0.32 divided by 0.0295, 10 to the power 0.26 divided by 0.0295, or 10 to the power 0.32 divided by 0.295. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. The correct answer is option B. So for the cell given in the question, the half cell reactions are zinc giving us zinc 2 positive plus 2 electron, oxidation is happening, and iron Fe2 positive plus 2 electron giving us iron, reduction is happening. And the overall reaction is sum of these two, which is zinc plus Fe2 positive giving us zinc 2 positive plus Fe. Now what we will do, we apply the Nernst equation. It will be E of cell is equals to E naught of cell minus 0.0591 divided by n log base 10 oxidized state upon reduced state, which is zinc 2 positive upon Fe2 positive. we have given the concentrations, we have given the value of E cell. So we just put it in the equation. It will be equal to this. And on solving, we have 0.2905 is equals to E naught of cell minus 0.0295 times 1. So therefore, E naught of cell is coming out as 0.2905 plus 0.0295, which is equals to 0.32 volt. Okay. Now at equilibrium, E of cell is equals to 0. EMF of cell is equals to 0. So in the Nernst equation, this becomes 0. So E naught of cell will become equals to this term. Now we know the E naught value. So we just put it in the equation. It will be 0.32 is equals to 0.0591 divided by 2 log base 10 Kc. And from here we can calculate the Kc. So Kc is coming out as 10 to the power 0.32 divided by 0.0295. We just convert this equation from this by using the log value or log property. Okay. So this is our final answer, and thus the B option is the correct answer. Okay. Now let's move to the next question. Question number 45. The standard reduction potentials at 298 Kelvin for the following half reactions are given against each. So we have given the some reactions and the standard electrode potential for the each of the reactions. What we have to find out? We have to find out the strongest reducing agent among them. Options are zinc, cesium, H2 or Fe3 positive. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. The correct answer is option A, that is zinc. So as the electrode potential is given, we just look at them and we can calculate that which is the strongest reducing agent. Basically, lesser the reduction potential, weaker the oxidizing agent, but stronger the reducing agent. Okay, so the strongest reducing agent will be which is having the lowest electrode potential value, which is present in the zinc case, and therefore zinc is the strongest reducing agent. Therefore, A option is the correct answer. Okay, let's move to the next question. Question number 46. Same quantity of charge is being used to liberate iodine and a metal. The mass of metal is liberated as 0.617 gram and liberated iodine is completely reduced by 46.3 milliliter of 0.124 molar sodium thiosulfate. Now, what is the total time to bring this change if 10 ampere current is passed through solution of metal iodide? We have to find out the total time. Options are 55.4 second, 25.2 second, 5.54 second or 16.8 second. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. The correct answer is option A, that is 55.4 seconds. So we have given that same quantity of charge is being used to liberate iodine and metal. So equivalence of metal will be equal to equivalence of iodine. And we can put it is equal to equivalence of hypo also, because all the liberated iodine is completely reduced using the sodium thiosulfate of this concentration, right? This is the reaction for the iodine and this is the reaction for the sodium thiosulfate. I2 plus 2 electron giving us 2I minus and 2s2O32 negative giving us S4O62 negative plus 2 electrons. So we just put the weight upon equivalent weight, that is equivalence of metal is equals to equivalence of hypo. We just put it. So equivalence of metal will be weight, that is 0.617 divided by equivalent weight, which is we have to find out, and equal to equivalence of hypo. Equivalence of hypo we can also write it as M times V times N factor, right? So M is 0.124 we have given. V is 46.3 divided by 1000 in liters and multiplied by N factor. N factor is 1. So on solving it, the equivalent weight is coming out as 107.47 because we used it in this equation, which is weight upon equivalent weight is equals to I times T divided by 96500. I is 10. It is given in the question. I is 10 ampere. So from this equation, T is only variable. So we calculate the T. T is coming out as 55.4 second. And thus option A is the correct answer. Okay. Thank you.